Right. So what happens is that we determine two things from the Schrodinger wave equation and the psi that we have. The two things we determine are, firstly of all, that the function is not damaged, and so it's a true eigenvalue equation. And so h psi is this value times psi, and so we can equate this constant that comes in front of the undamaged wave function is simply the energy. That's the first thing, that we confirm that that this all works good and proper, that it is an eigenfunction. But a second thing we determine is that the energy is dependent on two constants and whatever you have as a k up top there. So the energy is dependent on the k that you have over there. Now that k could be any number. So this is problematic in a way because we don't then have specific values of energy that are allowed. Energy of a particle that's free to move is not quantized, which is it's a bit of a disappointment, I suppose. If you're looking at quantum mechanics, it would be nice to explore a situation where energy is quantized, like in a hydrogen atom, where you have only specific energy values available to you. So this is interesting that for a particle free to move, the energy is not quantized. And there were a couple of other things I wanted to recap. And I'll just recap a bit further on. Oh, here we go. Is that from this wave function, we find that if you set some of the constants to 0, you find that you know the momentum, but you don't know where the particle is. And these two cases work. And there's a third case where you know the position, but you don't know the momentum. And that's led us to the Heisenberg uncertainty principle, where you can't determine two properties to perfect accuracy at the same time. There has to be some uncertainty in one as the accuracy of the other increases. Okay. And so just bear in mind that it's all in terms of this wave function is always in terms of probability. So where you don't know the momentum, in this case, what would happen is you would, if you ran some measurements of momentum on the particle, every time you measured a momentum of a particle, it would be something different. So there's no predictability in the momentum at all. Okay, and kind of at the end of it, I just try to explain how the wave function can be a superposition of different momenta, and if you have this superposition, then you start to localize your particle at a particular point. But to get a more accurate place for the particle, you have to have a superposition of many different momenta, which means that you lose all information about the momentum in order to get a position of a particle. Now, the next example that I'm going to do also has a particle that's free to move, but the particle's free to move inside a box. And I think I need to give a little bit of a roadmap where you go in this, because it's easy to lose track of the bits of information that come through. So what we're doing with the particle is we're confining it to a particular region of space. And this is very relevant to us as chemists, because in molecules, you will have an electron that can be confined to a molecule. And if that molecule's linear, then it is pretty much this situation where it can move between the ends of a molecule, but that electron can't move off the ends of a molecule, so it's prevented from moving in regions of space. So this is very relevant to us. And we're going to apply the results of this to real molecules. And this is the only part of solving the Schrodinger wave equation that I want you to be able to do as well, which is why I'm giving you the roadmap. So the way we're going to work with particle in the box is we're always going to start with the Schrodinger wave equation. And for the particle in the box, it's free to move. So you see the V term has been taken out. It's 0. It's totally free to move inside that box. But we will need to locate eigenfunctions of d2 by dx squared. And yes, at this point, our previous eigenfunction for that particle that's free to move would work. It would work, but I also told you that it could reduce to sine or cos. That would also work as well. But there's a good reason why we don't use that wave function for a particle that's free to move. And the good reason we don't use the previous wave function, and we have to go a lot simpler, is that we have to make sure that we have no breaks in the wave function, particularly at the ends. So over here, the probability of finding your particle outside the molecule is 0. Probability here is 0. So whatever happens in here, it has to decrease to 0 at the edge so that it's all connected. So 0 goes here, and then right at the point here, it'll be 0. And then you'll have something going on here, and it has to be 0 at the end. And the wave function we did for a particle that's free to move in space doesn't go to 0 at points. We have to use something that is a sine or a cosine, because we know sines or cosines. We can make them go to 0 at the points we want them to do. So we start with the Schrodinger wave equation. We need something that's an eigenfunction that's not damaged by d2 by dx squared. And we know that if you differentiate sine, you get cos, but you differentiate twice, you get back to sine. Or if you do cos, you get back to cos. Cos becomes sine, it becomes back to minus cos. So you don't damage sine or cos using d2 by dx squared. So these are good functions to use as wave functions. But of course, sine and cos don't work easily well. A function that will drop to 0 at the ends, cosine cosine is a nice big positive value at the edges. It doesn't drop to 0. But sine is the real one that you can make drop to 0 at the edges. Okay. And then, of course, because we have boundaries, because we've got a certain position of where it has to drop to 0 at L, we can then think about this constant k, and we can make sure that that k is such that it forces the wave function to be 0 at both of these points. Okay, and if we've got a decent wave function, we can always find the energy. We can put restraints on the sign to make sure it fits the boundary. And when you compare everything together, you get a lovely expression at the end that can be applied to molecules. Okay, so this is the roadmap where we're going. I'm going to take it step by step as we go through. And then what would be nice is after we've been right the way through, we come back to the roadmap and see where we've come from and where we've gone to and how we've got to this value over here. But of course, the starting point is the Schrodinger wave equation. Okay. So firstly of all, we have a Schrodinger wave equation, and eigenfunctions are of a form something like this. So if you were to fit this into that, you would find that it works quite nicely. However, if you look at a sine function, this is how a sine works, that at 180 degrees, it's at 0, at 360, it's 0. So you can see that a sine function comes to 0 at every multiple of 180 degrees. I'm working in radians here, so I'm not going to say 180 degrees. I'm converting that 180 degrees to radians, and so at 180 degrees at pi, it drops to 0, at 2 pi it's 0, 3 pi it's 0, 4 pi it's 0. So it's interesting to know that sine of any multiple of pi is 0. Cosine doesn't really work for us because cosine doesn't drop down to 0. So you want there to be no probability of the electron outside the molecule, and as you come into the molecule, you want the probability to raise up then from 0 to something. You can't have a big jump between having no electron outside your molecule and then a sudden jump and have your electron at high probability at the edge. That jump is not, it's not a natural jump, and so it doesn't fulfill the requirements of a wave function. And so we're not allowed to use cosine in this case. We're going to have to use a sine function, which means that if we're outside our molecule, there's no probability of finding our electron. As we come to the edge of a molecule, you can see that right at the one edge, it's a low probability of finding the electron, and you're more likely to find the electron inside the molecule. So the sine function works really well. So first things first, that although cosine works in the Schrodinger wave equation, it doesn't satisfy the boundary conditions. The boundary conditions will only ever be satisfied by sine function. But be careful, because the sine function at the moment won't work in a molecule of length L. We've got to somehow change the sign to make sure that it works for a distance rather than an angle, and that it fits within our molecule. So first things first, we have the Schrodinger wave equation. Second thing, a wave function could be ae to the minus kx, which we had before, but unfortunately that's got a cosine component, so we can't have a cosine component. So we are stuck with a very specific case. We are stuck with sine, and these edges have confined us to not allowing any function that can work as an eigenfunction. We've only got this eigenfunction that satisfies the boundary conditions. So step one, the wave function must be a sine function to satisfy the boundary conditions. Okay, so then the question is, how can we satisfy those boundary conditions? So we've chosen a sine function. So there's a lot on the slide, so imagine this as several slides, and so let's deal with them a bit at a point. So we've got a sine function. So the question is, does that sine function fit inside that box? And no, it doesn't, not at the moment. So let's see where our problems are with getting a sine function to fit in the box, because at the moment it'll be naught over here, but of course the sine will be not naught at the end of a box. And of course then you've got the jump when you go outside the molecule, and wave functions can't have jumps like that, and so it's not going to work. So on the left hand side, when x is naught, your wave function, when x is naught, psi is a sine of naught, and so it's perfect, it's naught. So this, the wave function on the left is naught at the edge of a box, and so sine is working beautifully at this side. See, it's working beautifully at the left hand side. It drops to naught at that point. However, it's not working well on the right hand side. So what we've got to do is we've got to force that sine to be zero, the value of the sine function to be zero at the right hand side of a box. Okay, so when we have, so if we replace x with L, so when x is L, psi must be zero. So when we're at L, when x is L, sine has to be zero. And it only works that sine of KL is naught if KL happens to be a multiple of 180 degrees. If KL is a multiple of 180 degrees, then the sine at that right hand side will be zero. So we're forced to make sure that KL, that K times L is a multiple of 180 degrees, which means that we can now solve for what the K is. And if we rewrite that K, we get n pi over L as that K. And so our wave function as it stands, psi is equal to a sine n pi over L x. So let's see if it works. Does this sine function work? Is it zero at the edge here? And is it zero at the edge here? Well, let's put x is equal to naught into that. And we've got the sine of naught which means that it will be 0. So the left-hand side works when x is 0. Now let's try the right-hand side. Let's try L. If you put L in there, the L's will cancel, and you're left with n pi. And we know the sine of n pi is always 0. And so we've got a wave function that works. We now know exactly what the wave function has to look like. Where it's not only an eigenfunction, but it drops to 0 at the edges of your molecule. So a particle in the box is really, it confines us to having a wave function that looks like this. Now, the most important thing that's happened to us is that n could be any number, but it has to be a whole number. What we've done in getting this wave function is we've introduced an n, a multiple of pi, and that n is a quantization. You have certain values of n that the wave function will work at. And so if you've got an electron and you place it in a box, then it has energy levels associated with it. And those energy levels come about because we forced the edges of that wave function to be 0. If you force the edges of a wave function to be 0, you have this n that comes in, and you're allowed multiples. And those multiples allow us to drop, those multiples allow situations where the sign will be 0 at the edges. Okay, so this is the wave function, and this wave function has come about by us having to get the sign to be 0 at the edges. Now, one thing we're not going to go into detail with is that the value of this constant a, and the value of it is square root 2 over L. That is a requirement because you want the total probability over the whole length of that cell to be 100%. So what we've got to do is we've got to scale the sine function to make sure that the total probability density is 1 over that. You can't have a probability of 110% of finding something in a certain region. The maximum probability you can ever have is 100%. And so psi squared, the sum of psi squared, or the integration of the sum of psi squared over all space has to be 1. And so that root 2 over L is to make sure of that, and it is called a normalization constant. I'm not going to ask you to integrate to find the value. Others have done it before, but we've got to normalize it so that the probability of finding your particle in the box is 100% and not any other value. Okay, so where have we come? I'm going to go back to the roadmap. So we have chosen sine kx, and because we've chosen sine kx as something that can drop to 0, we are forced to having kl as n pi, and so k is equal to n pi over L. So we know exactly what the form of a wave function is at this point. That's where we've got to at that point. Okay, so there we have, right. So what next? Well, we know that a sine of kx is an eigenfunction of a Schrodinger wave equation. And if you've got an eigenfunction of a Schrodinger wave equation, then it's possible then to calculate the energy. We can confirm not only that it's an eigenfunction, but we can also get the E value out of it. If we put the psi and the Schrodinger wave equation together, let's put psi into there and make sure it's undamaged and see what that constant is when you get it out. So I'm working on the left-hand side, and I've got a constant times d2 by dx squared of our wave function. And of course, know that d by dx of a sine kx is just k times cos of the function. And if you do a second, if you d by dx that again, the k comes out and it becomes minus sine. So d2 by dx squared of a sine function is minus k squared times the function again. So this is promising that it's going to work well as an eigenfunction and not be damaged by d2 by dx squared. Okay. So when that works, when you calculate it, you find that the constant you get in front of your function is h bar squared k squared over 2m, and that h bar squared k squared over 2m is equal to the energy. And so we can relate those together, we can relate those energies, and we can get the energy is equal to h bar squared over h bar squared k squared over 2m. You can rearrange it to get k, and you'll find that your wave function could also be written in this way, where square root of 2me over h bar squared is the k in this situation. But really it's important, don't worry about this part. What's important is that your energy can be written as a term in there. On our previous slide, we had another expression for k. And it'd be interesting, if we took that other expression for k and put it in here, we might be able to get the energy in terms of the n that k is represented with. So using the Schrodinger wave equation and using that psi tells us the value for the energy of a particle that's described by that wave function. Right, so this is important. If I go back to the previous slide. Okay, so couldn't we use cosine with a phase shift as a question? That is a very, very good question. Could we use cosine with a phase shift? Well, cosine with a phase shift is a sine function. So yes, we can use cosine with a phase shift, but it has to be perfectly phased, so it is a sine function. And why does the h value at the top not have a squared value? So let's just see. Did I write something wrong? I'm not sure where that question is.
Sorry, sir. It's 2 slides down. I think that I was confused. 2 or 3.
Over here.
Yeah. No. 2 down.
Okay.
One more.
One more. Okay.
Yeah.
No,
at the.
Just hang on. We haven't got quite there yet. Oh yeah. Oh, my apologies. I think I've left out. My apologies. I'm trying to fix mistakes as I get to them. Well done for picking that up. We've got to have that h bar squared. Apologies on my Schrodinger equation. Please make sure that it is placed correctly.
Okay, thank you.
Okay. What is the purpose of n times pi over L? So let's go back. That's a very good question. Let's go back. What's the purpose of n pi over L? So over here, n pi over L is a requirement if we want to make a sine function go to 0 at L. So you can imagine that if you've got size a sine kx, if you put L in there, say L was 5 angstroms, and you put 5 angstroms in there, how could you make this value of k be such that that 5 would drop this all to 0? And the way to do it is to have n pi over 5 to force it to be 0, because if you've got n pi over 5, the 5's cancel and you're left with sine of n pi. And from this graph, you see sine of 1 pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, sine of 4 pi is 0. So that's a good question. N pi over L scales the sine function in space so that when you reach L, the L's cancel out and you're left with n pi. You're left with something that will force the sine to drop down to 0. Okay, so what happens is we've got an energy on the one side and we've got a k on the other side. So this was what we got from the forcing the boundaries to go to 0 for the sine. This is we got when we put the psi into the Schrodinger wave equation, when you put that together. So if we put the k into there, then of course k squared, we have to square pi and n squared and L squared. But remember that h bar is h over 2 pi. So h bar squared is h over 4 pi squared. So a lot of pi's. So h bar squared is h squared over 4 pi squared. That's h bar squared over there, which means that pi's are going to cancel out. And then in our answer, we don't have h bar anymore, but we're back to Planck's constant. The energy level is dependent on the n that came from k over the length times h squared. Okay, so what happens at the end when we compare our two ways of looking at the system, one with Schrodinger wave equation, one with looking at the requirements for the sine function, is that we get a value for energy that is dependent on whatever n you chose. And the lowest energy level is 1 in this case. So what does it look like? What does the wave function look like when n is 1? So here is the wave function. So when n is 1, what we have is, this is what it looks like. And you can see there's a region of high probability. If you were to square this, there's a region of high probability at the center of a cell and low probabilities towards the outside of the box. The next energy level, you can see when you square, there are two regions of high probability, and then there are three regions of high probability for n is equal to 3, and as it goes up. So it's interesting that we now have the energy levels, and the energy levels will define how those particles move, how the particle moves in the box. So it can't just have any energy value, it's got to have these specific energy values, and we now have quantum mechanics. We've got the quantum, we've got only set energies are allowed. Any other energy levels would not drop to 0 at the edge. You can see it's 0 at the edge, n is 5, and it's 0 at the other side. N is 4, it's 0 at that side, drops to 0 there, and so on. Any other energy values are not allowed because your wave function is not going to fit. And so you've now got quantization in that box. Okay, an interesting point is that the lowest energy allowed is n is equal to 1. That particle cannot have we can't have n equals 0. I'll speak a little bit about that. Okay. Having to fit the wave into the box using n pi over L is what leads to quantization. It's interesting, this is another place where we cannot calculate the momentum. Really, what's happening with this particle in the box is that if you, maybe if I can just carry on, if there are strategies for calculating momentum with a wave function like this, but it ends up with two answers. It ends up with a positive momentum and a negative momentum. So what's happening is that particle is rattling around inside that box. It's going forward and backward in that box. And so we cannot determine the momentum. It doesn't have a specified value of momentum in that box. And it's interesting that the 0 point energy is n is equal to 1. Now, this is partly, the Heisenberg uncertainty principle creeping in again, because by confining a particle to a region of space, you're becoming quite certain about the position of the particle. So, if you're becoming certain about the position of the particle, then you're going to become less certain about the momentum of the particle. And of course, if you're not certain about the momentum of a particle, you can't say that it has 0 energy. Okay, so you can't say that. And so, of course, this particle can't have no energy. Instead, it's got a 0 point energy where n is equal to 1. Okay, So that there is solving for a particle in a box. We're going to use that in a moment, but I want to go back to the roadmap. Here's the roadmap. Sorry, I think I missed a squared in on the Schrodinger wave equation. Please check that I've got that correct. We need something that's the eigenfunction of d2 by dx squared, and sine is the only thing that works. And we have to scale the sine so that at the boundary, KL, at the boundary, at this right-hand boundary, we have a multiple of pi, which places restrictions on the k that we've got. So k of x, the constant, whatever it is, we've now restricted it. It has to be a multiple of pi over L. Then we've now got an expression for k. We now have our wave function that we can put in the Schrodinger wave equation. We put it in the Schrodinger wave equation, then we get our energy as being this value. And when you compare the k there and the energy value we get, we find that the energy is dependent on the n, and we can simplify it. The energy is h squared n squared over 8ml squared. So this is a complete solution of a Schrodinger wave equation in one dimension for a particle in a box. Now, as a chemist, we can now use that in real situations on real molecules because we can now get some useful information simply based on the energy of an electron in a molecule. Can I show you? So, for example, have a look at this molecule, this conjugated alkene. The pi electrons are quite nice. You've got sp2 hybridization right the way through. So the pi electrons are free to move from one end of a molecule to the other, but of course they can't move off the end. We've confined that electron to a one-dimensional box, and the dimension of the box is 994 picometers. But there's not just one pi electron. Can we count the pi electrons? We're going to have 2, 4, 6, 8 pi electrons. And of course, those 8 pi electrons are going to fill the first 4 energy levels. So in our box, when we look at our box, in n equals 1, those first 2 electrons will go into the bottom, and then the next 2 electrons will go into the next, and so on. And we've got 4, so the first 4 energy levels are filled. And if you shine light at it, if you shine light from the UV vis spectrum at it, the maximum absorption by the molecule is going to be associated with a photon kicking this electron from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. So a light coming in is going to push an electron from energy level 1, 2, 3, 4 to energy level number 5. But do we know in a box what a value for those energy levels are? And yes, we do, because in a box we know H, that's a Planck's constant. We know the mass of the electron, we know the length of a molecule, and we know the energy level. We know energy level 4. We can calculate the energy for energy level 4, and we can calculate the energy level for energy level number 5. We have all the information we need to calculate an exact value of energy for this molecule. Okay, and so we can do that, and I've done it. So on the slide, you can see that I've managed to find the mass of an electron. I've converted 994 picometers to meters, and I've found H as the Planck's constant. So you can see that in that equation, I calculate E4 is where I put n equals 4, and E5 where n equals 5. You find those two values, I've done that, and then you subtract them together and subtract them from each other, and the difference I get is 5.49 times 10 to the minus 19 joules. So we know that the difference in those two energy levels between 4 and 5 for that particular situation is 5.49 times 10 to the minus 19 joules. So if I can go back here, between this energy level and that energy level for that particular molecule, we know its exact value for that. And so what we can do then is if we know the exact difference in energy, then we can work on the light that kicks it from one energy level to another. If the light has the same energy coming in, then of course we can work out the frequency of light and the wavelength of the light, and we find out that the wavelength of light that does that, we predict it from our particle in the box. We predict it to be 362 nanometers. So this is a real application of quantum mechanics to a real life situation where we've got electrons that are confined to a region of one-dimensional space. Okay, are there any questions? Okay, so I've got one final comment on particle in the box, but please can I ask you to do two things. Please have a look at my annotated slides where I've put comments on. Have a look at the video for the lecture at the end of a lecture. And could I please also ask you to have a look at TUT problems where this is used. So there are examples in the tutorials where this is used. So you can have that as a practical example. So final comment is that particle in a box is quite interesting if you're forcing it to stand. So the molecule, you can force the molecule to stay inside the box. However, there are situations in chemistry and in other places where the barrier is not infinite, and the barrier can be incredibly high. And even though you can see the amplitude, even though the energy might not be as great as the barrier, the wave function ends up not being zero outside the box. So if you were to take the edges of a particle in a box, and instead of having infinite potential, have a finite potential, even if it's a very large potential, what can happen is that the wave function then just deteriorates through the barrier, and it means that there's you've got a probability of finding something outside of the box. And there are cases, certainly with isotopes, and certainly with reactions where you expect that the containment will maintain whatever it is inside a certain region. But of course, because the barrier is only finite, there's a probability of finding something outside. So tunneling is, even though psi decreases exponentially through the barrier, there's still finite, there can still be a finite probability of finding your particle outside where you expect it to be. So tunneling is quite an interesting situation in chemistry. So please go back to the roadmap, make sure you use the correct Schrodinger wave equation in that, and work your way through to make sure that you end up with the energy value, and then see if you can apply that to a real situation, to a real molecule where the energy is jumping. Okay, any questions? Okay, so that is where I'm leaving it for today. And please, my email is open. If you've got problems in the prac, please let me know. I'm getting together an alternative to the Perl scripting prac. That's going to take a few days to complete, but that will be available. Any questions on the lectures, any questions on the pracs, please contact me and I will respond as soon as I can. Okay, thank you.
There is a question that I just asked.
Okay, yes.
How do we submit the pracs?
Email them to me.
Okay, so we have to email. Okay, cool.
Yeah. Okay. And the thing is that when some people don't have access to the pracs yet, and so I will be working with those who don't have access to the prac on their return. So I'll work carefully with them on their return, which means that although I'll put your marks onto Ross now, I'm only going to publish it when everyone has done the prac. So I don't want to disadvantage people who don't have access to the system right at this moment. So just be aware and that your mark does go into the system, and I'll let you know what the mark is, but you won't see it directly on ROS. Okay. No more questions?